Welcome to my classroom. In this lecture number 10, we will discuss about fermentation reactions and mechanism of enzyme reactions. In lecture number 9, we have seen introduction to enzymes and introduction to fermentations. So in this lecture number 10, we will discuss about fermentation reactions, how the mechanism of enzymes will vary, and we'll compare when the fermentation reaction is involving a microorganism and it is involving a enzyme. How it is going to vary will be discussed in this lecture. Ready? So in lecture number 9, we have discussed about introduction to enzymes and introduction to fermentation techniques. In this lecture number 10, we will discuss about enzyme kinetics. So before getting into enzyme kinetics, let us recall what we have learnt in our CRE course, that is chemical reaction engineering course. Okay, so we have seen initially what is chemical kinetics, what is molecularity, what is order of the reaction, what is molecularity. It is the number of molecules involved in a reaction in an elementary step or a single step, or in each step of the reaction, number of molecules involved. So for example, one molecule is involved in the reaction, it is called unimolecular. If two molecules are involved, it is called bimolecular reaction, or if three molecules are involved in a reaction, then it is trimolecular reactions. Okay, so this molecularity will be always in whole number. Okay, it will not be in fractions. Okay, and it is a theoretical value based on the stoichiometry, number of moles of reactants involved. So we are defining this molecularity. Whereas order of the reaction is not a theoretical one, it is a experimentally determined value. For example, if A plus BB giving RR, then we have, it's not an elementary reaction. If it is elementary reaction, the rate equation can be easily written as minus RA equal to K into CA power alpha CB power beta. If alpha or beta are the order of the reaction with respect to reactant A and B, if it is elementary reactions, this alpha can be equal to the number of stoichiometric coefficient of A, that is small a. Similarly, beta can equal to small t. Okay, that is for elementary reactions. For non-elementary reactions, this alpha and beta can be anything. It can be first order reaction, second order reaction, or it can be zero order reaction, or even it can be negative value also, or it can be even fractional value are also possible. So all these things are possible with respect to order of the reaction. That is the difference between this molecularity and order of the reaction, where order of the reaction can be fraction, it can be negative also, whereas in case of molecularity it should be in a whole number, right? Fine. So now after this, what we have seen different type of reactors we have seen, right? We have seen the plug flow reactor, we have seen CSTR, all that. Okay, so how these rate equations are related to each other with respect to rate of A, rate of B, rate of the reaction for A, rate of the reaction for B. Before that, we should know how this rate of this reaction, rate of the equation, rate of the reaction can be defined in various ways. It can be defined with respect to volume of the fluid, right? So based on volume of the fluid, minus RA equal to 1 by V into dNA by dt, where Na is the number of moles of A disappeared, dt is the time taken, right? Similarly, it can be even defined with respect to mass of the solids involved, right? W. So that way also minus RA equal to 1 by W into dNA by dt, right? So that way also it can be defined. And if it is involving interfacial surface area, S, in that case also minus RA equal to 1 by S into dNA by dt. So that way also it can be defined. Also it can be based on the volume of the reactor, right? So in that case minus RA equal to 1 by VR into dNA by dt, right? So there is one more way it can be defined, that is, it is based on the volume of the solid involved, Vs. Okay, so minus RA equal to 1 by Vs into dNA by dt. So where again dNA is the number of moles of A disappeared, dt is the time taken. So these ways this rate equation can be written with respect to based on various things, right? The volume of the fluid, volume of the reactor. Remember, for elementary reactions or for homogeneous reactions, this volume of the reactor will be usually equal to volume of the fluid. So that way they are equal. Okay, and this rate equation with can be written for each raw material or the reactant involved, right, or the product formed, or even for the intermediates involved or the molecules formed in between. So the rate equation can be written for them, how they are related. So they are related based on the their stoichiometric coefficient. For example, 1 mole of A plus 2 moles of B gives 3 moles of R. So how the rate equations are related. So minus RA by 1 equal to minus RB by 2 is equal to plus R3 RR by 3, because A 1A plus 2B is giving 3R. Okay, where R is capital R. So that way also we can relate the rate equation. So that way when you say that you can relate it in terms of rate constant also. Okay, so that is the thing, and we know this rate of the reaction. Rate of this reaction is a function of two type of term based on terms involving concentration, terms involving temperature. So in general it is a function of concentration and temperature. So these terms involving concentration can be there, terms involving temperature can be there. So the terms involving temperature are arrived using various theories proposed. One is Arrhenius theory is there, transition state theory is there. We will be making use of them to get these terms involved. Okay, with respect to concentration, it depends upon the order of the reaction, whether it is elementary reaction, non-elementary reaction, or how what are the intermediates formed. So these rate equations are going to be like it can be complex also, or it can be as simple if it is an elementary reaction or homogeneous reactions. Okay, well, this rate of these reactions are a function of concentration dependent terms and temperature dependent terms. Concentration dependent terms means it may be depending upon the nature of the reactants, depending upon the concentration of the reactants, and the physical state in which these reactants are present, and depend upon the catalyst presence and the concentration of the catalyst present. Okay, and it depends upon the temperature of the system, reaction system, the pressure of the reaction system, right? So these all will affect the rate of the reaction. Okay, well, between elementary reactions and non-elementary reactions, elementary reactions are single step reactions, and these rate equations are very simple to express. That you will have this order of the reaction, that alpha beta value directly proportional to this E and B values, that is the stoichiometric coefficient values. Whereas in case of non-elementary reaction, it is a series of elementary reactions involving intermediates like free radicals, ion intermediates, or it can be a molecule formation, or it can be a transition complex. So based on that, we are going to have a rate equation. It's going to be more complex in nature. Okay, so example, even our enzyme kinetics is going to fall under the category of molecule formation. Okay, and between these chain reactions and non-chain reactions, chain reactions are will have three steps primarily. That is, like there will be a propagation step, there will be initiation, propagation, and termination steps. So initiation step will be there, propagation step will be there, and there will be termination step in case of chain reactions. Whereas in case of non-chain reactions, there will be an intermediate formation which will be very fast reaction. So there will be a quick intermediate formation. Then that intermediate will further proceed to form a series of products. Okay, there may be a number of steps involved in it. So that is called non-chain reactions. So these enzyme reactions will come under the category of non-chain reactions also. Okay, so next, if you look at one of the assumptions that is made in this type of intermediate formation is that pseudo steady state approximation or pseudo steady state hypothesis. Okay, what is that pseudo steady state hypothesis? Here, when you have n number of reactions are there, and if the lifetime of the intermediate formed is very short, that is at any time the concentration we will not be able to easily measure. Okay, for example, an intermediate is formed, if we have some instrument, we should be able to detect it, right? So that means what? The rate at which the intermediate is formed and the rate at which the intermediate is further proceeding or disappearing into another product is going to be equal. So then what is the net rate of formation of that intermediate? It is going to be 0, right? So when the enzyme concentration at any time is when any intermediate is formed and its concentration is very low, it means that that the rate at which it is forming is equivalent to the rate at which it is disappearing. Hence, this net rate of formation of this intermediate is equal to rate of formation of intermediate minus rate of disappearance of intermediate, which is equal to 0. Therefore, the net rate of formation of an intermediate is equal to 0, and this approximation is called as pseudo steady state approximation. Okay. Now, if you look at the batch reactors, in case of batch reactors, what is the performance indicator? What parameter is used to assess the performance? For example, I want to have a certain conversion. The parameter which needs to be fixed is time. So time is the parameter important in case of a batch reactors. And if you are going to operate in a continuous reactor, we have seen CSTR and plug flow reactors. For these two reactors, we have two performance indicators. What are they? One is space velocity and space time. Okay, what is space time? Space time, we have a reactor volume, right? And how much feed can be processed in one reactor volume. And there is another case, in a unit time, how much of the feed can be converted. So based on this, we define space velocity and space time. Okay. So we have seen that two performance indicators for the continuous reactors are space time and space velocity. What is space time? It is the amount of it is the amount of feed that can be processed, amount of reactants that can be processed per unit volume of the reactor is called space time, which will have the unit of time, that is like minutes, seconds or hours. Okay, so that we can have, and this can be obtained by dividing volume of the reactor by volumetric flow rate. So volume of the reactor is meter cube, volumetric flow rate is meter cube per second. So if you divide these two, then you get the final unit is going to be meter cube will get cancelled. You have second as the unit. So tau, it is represented by the symbol tau. Okay, so tau is equal to V by V naught, which is in unit of in seconds. Okay, and we have space velocity. So it is like per unit time, how much reactant can be processed. So that is called space velocity, and it is the inverse of space time. So S, it is denoted by the symbol S, and S is equal to 1 by tau. Okay, so that is how it is defined. And we have even derived performance equations for CSTR and PFR in our CRE course. And we can write that tau by CA naught equal to dXA by minus RA is the performance equation for CSTR, which means that when you plot 1 by minus RA versus XA curve, so if you have the plot, how to find the volume of the reactor for CSTR? It is going to be rectangle shape, right? So for a given conversion, you will draw a line up to the curve and take to the y-axis, where the area under this rectangle is gives you the volume of the reactor. So we are considering ideal reactors. Okay. So similarly, if you consider plug flow reactor, so the equation that we have is tau by CA naught is equal to integral dXA by minus RA. So in that case, integral in the sense it is area under the curve. So when you plot a graph of 1 by minus RA versus XA, and the curve is there for a given conversion, how will you determine the volume of the reactor? It is going to be the area under the curve. Okay, so that way for a same set of type of reaction, this is for any order greater than 0, let me say. So for elementary reactions or for zero, so the reactions can be 0 order, first order or second order. So if you consider a 0 order reaction, the volume of the reactor required for a CSTR or a PFR is going to be the same. When the order of the reaction is greater than 0, that is for any order of the reaction n greater than 0, so the area volume required by the PFR is going to be less than the volume required by the CSTR. So that means we are going to get more conversion if you have, say, we'll need less volume of the reactor in PFR, that is plug flow reactor, for a given conversion. Okay, so all this for non-catalytic reactions. Okay, it's for any catalytic reactions also. Okay, but if it is autocatalytic reaction, we are going to have different scenario. Okay, because in case of autocatalytic reactors, we are going to get a curve of 1 by minus RA versus XA in U shape. Okay, when you have a U-shaped curve, what will happen? it may not be feasible if you consider for a given conversion. If it is very low conversion, we have one set of reactor is preferred. If it is intermediate or if it is a very high conversion, one reactor is preferred. Let me say if you 1 by minus RA versus XA in U-shaped curve data we have, curve we have. So then for low conversions, which is better, rectangle or area under the curve? For low conversions, which one is better? For low conversions, when you have curve like this, I have here. So rectangle is smaller. Volume required for the CSTR is smaller in compared to PFR, because for PFR it is area under the curve. Okay, so that way CSTR is preferred for an autocatalytic reaction when the conversion is low. Okay, when the conversion is very high, so again in the U shape at the end it is there, means, so in that case area under the curve is less or rectangle is less. Rectangle is more and the area under the curve is going to be small. That means the volume of the reactor required by the plug flow reactor is less than the volume of the reactor required by an CSTR. So that way for very high conversions, PFR is preferred. And if you other alternative is, if you want to go for a combination, which one followed by which should come? So that means up to that maximum conversion rate where you get the peak, okay, when the slope is 0, up to there CSTR, and after that plug flow reactor is preferred for autocatalytic reactions. So see, remember I'm talking about all this again, even though we have learned it in CRE course, because most of our enzyme reactions or fermentation reactions are going to come under this category of autocatalytic reactions. Yes, okay, so we are going to make use of this autocatalytic reaction concepts in our enzyme in this particular course. That's why I have been recollecting what we have learned in our CRE course. Okay, so now this is the case, right? So we have autocatalytic reactions and we have three preferences, right? For low conversion, CSTR is preferred. For high conversion, plug flow reactor is preferred. Or if you want to have a combination, up to this peak where you have maximum rate, we will have CSTR followed by PFR is preferred. Okay. Coming to fermentation processes, these fermentation processes can be carried out using microorganisms such as yeast, bacteria, algae, protozoa, molds, right? Or it can be done in other way using enzymes, right? So these fermentation reactions either using microorganisms or yeast using the enzymes. So we are going to have a catalytic type of reaction taking place. Okay, for example, if you substrate, we are having a substrate of A plus a small amount of microorganism or a enzyme is taken concentration C, then we have a reaction of A plus C becoming product R plus C again. So if it is microorganism, the C amount is going to be more because these microorganisms are multiplying in the system, right? So that way, so this is similar to a autocatalytic reaction taking place. So what is actually a series of events that is taking place when you use a batch reactor where a small amount of microorganisms and initially certain amount of substrate concentration is kept. So series of event taking place is, so we have substrate in the system to which this microorganism in small quantity is added. So initially there is more substrate and less microorganisms. So the rate of the reaction is going to be slow because the substrate is more but the catalyst is less. Okay, so that way the rate of the reaction is going to be slow. But what happens with respect to time, this microorganism will propagate or it will be multiplying, it will reproduce and microorganism will grow in numbers. So that means our catalyst amount is increasing with time. So as the catalyst increases and sufficient amount of substrate is there, so what will happen to the rate of the reaction? So this rate of the reaction will slowly increase, right? And it is going to reach a maximum also. The rate of the reaction will reach a maximum point also. After that, what will happen? You have more microorganisms present in the system, but the amount of substrate is consumed already. So as the microorganism is there, they need feed, right? They need food to survive. But the substrate amount is getting reduced. What will happen to the rate of the reaction? So the rate of the reaction will start slowing down and eventually it will become zero. And this is a typical autocatalytic reactor, right? So this is what a autocatalytic reaction. This is what happens in a autocatalytic reactions. Okay, so that's why we are going to study this type of thing. But when you compare between these microorganisms and enzyme reactions, two things is there. When you consider these microorganisms, the quantity, the amount of microorganism, the concentration of microorganism in the system is ever increasing. Okay, and then goes down because substrate is not there, eventually it will decrease. But whereas in case of enzymatic reactions, we are initially going to feed some enzymes, and that enzyme concentration is going to be E naught. Okay, so that enzyme will take part in the reaction, but it is acting like a catalyst. So it is like a catalytic reaction, because when yeast is used, then quantity, the amount, it is not going to reproduce or it's not going to multiply. The same amount of yeast will be present, but either in the form of yeast or it will form some intermediate complex, because the reaction taking place when enzyme is involved is A plus E becoming AE. It may be a reversible reaction. Then that AE complex or ES complex, if yes, CRE we use A, in biochemical engineering we are going to use it as substrate, so yes we will use, so S plus E will form SE complex. Okay, so that ES complex is formed, enzyme E, substrate S, E plus S will form E dot S, that is ES complex is formed. It is an intermediate or molecule, intermediate molecule is formed. So this ES will further proceed to form the product R or P, then enzyme will get separated out, right? So product plus enzyme, so that's what happens. I repeat, enzyme will react with substrate to form an intermediate ES, then this ES will proceed further to form product and enzyme, or this complex ES may return to back to E plus S, so that E plus S becoming ES is a reversible reaction. So we are going to have a forward rate constant and a reverse rate constant. Then we have K2. So let me say K1, K minus 1, and then K2 are the rate constant for this one. So E plus S, forward and backward ES, then that ES is further proceed to form product plus enzyme. Okay, so then what will be there when we collect the product out, what are all will be there in the system, in the mixture, product mixture? We are going to have product, we are going to have enzyme, we are going to have unconverted substrate, right? And if there is any byproducts form, that also going to be present. Okay, so that way, so we are going to have this both type of reactions, involving microorganism, we have to handle it like autocatalytic reactions. If it is involving enzyme, we have to consider it to be a catalytic reaction and proceed further to get the mechanism of these reactions. Okay, but whatever we have discussed all this, if we have considered a single substrate and single enzyme system, right, or a single microorganism system. If you consider a multiple substrate system and multiple microorganisms or multiple enzymes are present in a system in a mixed reactor, so that is, it is going to be a mixture, right? Instead of single substrate and single enzyme, it is easy for us. If it is a single substrate and single enzyme, it is easy for us to proceed with the thing, because we have learned the derivations, all that in our theory course also, easy to do that one. Okay, moreover, when the stoichiometric coefficients are fixed, for example, if the ratio of substrate and enzyme are fixed, then we are going to get, if you repeat the same experiment for the same amounts or in the same ratios, we are going to get the same output, same amount of product will be formed. The conversion is going to be the same. So scaling up is easier when you use a single substrate and single enzyme system. Okay, whereas if it is a multiple system where we have n number of substrates and n number of microorganisms present in it, so then obviously it is going to be more complex. And when you do it in small scale, we have 3 substrates, 3 microorganisms, and in small scale I got a result where I have conversion of production of a particular product. Okay, I try to scale it up to bigger level production. What will happen at that stage when you are doing it in large scale? Since it is more complex, in small scale I got a result. When I'm doing it in large scale, when I have multiple substrate and multiple microorganisms, when I do scaling up, some other product may be predominant. In small scale, one product is one microorganism is very active in small scale operation, and one substrate is consumed more. But when I do it in large scale, some other microorganism will overtake. Say, for example, if you play people playing in domestic cricket and when they are taken to international match, in domestic cricket matches like Ranji trophies, they might be scoring very well. Okay, when we put them in international match, they will be coming and getting quickly out. They may not get enough chances like that, right? So like that situation happens when you have multiple culture or multiple microorganism and multiple substrate system. Their performance, one may be leading in small scale operations, and when you are doing it from pilot to large scale operations, the performance or some other microorganism will taking over. For example, Shardul Thakur was a very good bowler when you are doing in domestic. When you put him in a test arena and given chance, he is scoring like a regular batsman, right? So like that, some other microorganism will overtake when we are taking from small scale to large scale for a multiple enzymes or multiple microorganism or multiple substrate system. So for a single substrate, single enzyme system, it is easier for a single microorganism system. It is easier to scale up from small scale to large scale. Okay. So if you consider any fermentation reactions, as I told you, so this concentration of this microorganism is going to change with respect to time, whereas for enzymes, the concentration is going to stay constant. So we'll discuss them using board. Okay.
There is an issue in uploading 1 hour video and uploading it as a separate video. So this lecture is continued in next video also. Please watch it.